second, we proceed to the last presentation in this section. Professor Yuan will talk about thermomechanical fatigue, nickel-based superalloys, and we are looking forward to your presentation.
Good. Thank you, Hashmana. I changed my title slightly to fit the session topic here, and I give up the details about constructive model and change to the so-called fatigue assessment. And we are going to go to some details about so-called thermal gradient mechanical fatigue. That is something different from conventional case. We're talking about you have both temperature gradient and thermomechanical coupled in the case. Just few. I'm from Tsinghua University, School of Aerospace Engineering. My specialty is research area is actually aero engines. Okay, just a few words about the introduction and motivation of the work, and then go to some details about fatigue and fatigue tests and assessment and so on. Then we're going to talking about model. We're going to develop constitutive model and fatigue model and final conclusions. Good. As I said, I work on aero engines. If we talk about aero engine, we know okay, the temperature is very high, and usually we said okay, in combustor the temperature exceeded 2,000 degrees C already, but the material temperature cannot be so high. If usually actually all aero engines use so-called nickel-based alloy. This is nickel-based alloy. What you see here is actually the so-called turbine, high-pressure turbine blade. This material is of single crystal nickel alloy. That material can be used up to 1,000 degrees C or 1,100 degrees C, the highest temperature we can use. As I said, but the environmental temperatures are around about 2,000 degrees C. Therefore, we have almost 1,000 degrees C temperature difference between environment temperature and the material temperature. Therefore, we have to cool down. Therefore, we introduce into cooling air into the blade and the field cooling film and so on to keep the material temperature down lower than 1,000 degrees C. So that is the absolute maximum we can work. Therefore, in such part, we have very large temperature gradients in the component. It's not only around the hole, but also within it. And the stress in the blade is not high, but we have actually both temperature coupled with like mechanical load. Therefore, the problem actually is coupled with thermomechanical and additionally temperature gradients. That is the case. Right now, actually, more engine makers just use the actually isothermal method to design components. Since we believed the material's property or fatigue property of material at higher temperature should be worse than low temperature. That's what we believe. The situations actually could be slightly different. There's many research published in the past years. They found and thermomechanical fatigue property of material can be much worse than higher temperature other thermal fatigue property. Therefore, it becomes a problem how to quantify the effect of the thermomechanical coupling. Additionally, we have in the case so-called temperature gradient. Additionally, we introduced that thermal stress into the component, and how to quantify the effects becomes also a severe problem. Okay, that is the motivation what we want to tell you. And now we come to our test facility. We establish a special test facility. That is actually what you see. It's not so much, but I can tell you that this is a conventional machine here. This furnace is actually heated by radiation. We use the lamps to focus the lamps on the specimen. We can heat up specimen very quickly, within seconds actually. And maximum temperature, we do not measure the maximum temperature. Anyway, we can bring material to melt immediately, in seconds actually. And therefore we test actually, in our case, different materials. In the present talk, I'm going to talk about just conventional nickel-based alloy and working temperature for that super alloy is limited up to 650 degrees C. That's for the material. Okay, we test also other material, for instance, the CMC, the ceramic metal composite, or single crystal super alloy. In that case, temperature is higher. What you see here is actually a picture we made. Actually, as you see the specimen here, go around actually the radiation. Actually, the oven temperature is not high, but you need to focus here, and the specimen temperature becomes very high. You can change the temperature very rapidly. That is specimen we manufactured. But actually, the diameter here, external diameter is 12 millimeter. Thickness of the tubular specimen is 1 millimeter. The reason is actually lower than 1 millimeter becomes very sensitive to the manufacturing, and the real blade, the thickness of the material is around about 1 millimeter. Much less than 1 millimeter becomes difficult. Good. That is the length of it is 120, and runs more. And okay, that is specimen. That is the temperature curve you see. You see actually here temperatures around the linearly function of time. That's time. That actually each load takes around about here 180 seconds. That is actually around about 4 minutes, actually 4 to 5 minutes to one cycle. And just due to the heat transferring, it takes time. And this thermal load will be combined with mechanical load. That means mechanical load is all in same state actually. Okay, we can change the so-called phase angle between mechanical load to temperature load here. And in our specimen, we can, of course, if we're talking about the TGMF, we have cooling, additional introduce cooling into the tube to introduce the temperature gradient. Okay, then you pump actually the cooling air into it, and then to introduce the mechanical temperature gradient. Okay, but this actually we need to measure the temperature in the inner surface becomes towards a very difficult task actually. We try to measure it. For instance, bring our thermocouple on the surface and try to measure temperature here. This specimen here, what you see here, that we found the measured value is very sensitive to your pressure on the surface. Actually, thermocouple measured actually the average temperature around this thermocouple. Therefore, the value what you obtained is actually not a real material temperature, but it's environmental temperature. Therefore, the value becomes nonsense actually for us. And therefore, we go to the computations. We introduced actually established FEM mode and just try to calibrate. Okay, calibration of course happens after external side, internal side. Internal side we can measure that, but external side we can measure exactly, and then change actually the cooling air and so on. Try to find the correlation between the external and internal temperature. Okay, we can calibrate based on stress distribution and so on. Okay, that is the test facility we used now to test. So what I mean, we are going to talk about both thermomechanical fatigue and thermal gradient mechanical fatigue, both cases. What we obtained actually, what you see here, that is TMF result. That is all result actually in phase case. Now as thermal actually, and the red value is actually finished by Indian colleague. He published the work here, and that is the NASA from NASA. And in that sense, since we use actually effectively rather different materials. Okay, all of us use the Inconel 718. Inconel 718 is the very most popular nickel-based alloy in air engines, but the manufacturer are different. Therefore, we cannot guarantee it was the same material. And that I would say the difference between materials, they are not so sensitive in the case. Significant larger deviation, we see the effect of loading. I mean, you see what here, that is the strain control case, mechanical strain control test actually. What you see here is actually a mechanical strain, equivalent mechanical strain, and the horizontal axis you see live of it. We performed, as I said, a mode action case. Therefore, you see in phase, that's the in phase, out of phase. Out of phase means actually you see the maximum temperature, but in that case you have minimal mechanical load. They are actually exactly 108 degrees shifted. And that means we see what you see here actually, that is in phase case. This line is actually the isothermal. And that is out of phase. Red line the TGMF, that's the TGMF here. In phase TGMF here. And you see the difference between them, almost 2 decades, right? And okay, you see the life cannot be so long. Therefore, the reason actually that due to very low speed we can perform in TGMF test. And okay, that is the TGMF out of phase, and that is the actually with so-called with TBC, the introduced so-called thermobaric coating on the specimen. Therefore, of course, life becomes better. But you see that the difference to the other thermal is still significant. Okay, and the point actually, the question is how to bring all these experiments together. That's the point for us. The reason is actually what we know in reality is actually we just know temperature, we know the mechanical load in design, but the life assessment actually based up to now we just use aerosol theory. We use this curve, but these results show you that this line is not conservative. It's very dangerous. Difference came up to 2 decades. Therefore, design becomes nonsense to what we did. Therefore, the question how to quantify the thermomechanical or the thermal gradient mechanical effects into your life, your life prediction. Okay, now we going to see, we use at first the different multi-axial fatigue model to test. We chose several ones, Plasticity, Brown-Miller, Epsilon Tupper, 2 different Liu model. Liu is actually we introduced the energy model, and rather new model. Zameric model is actually specially developed for TMF 3 years ago. And we test all of them. The show you go through quickly, and the comparison of different model with results, external results. Here you see external results. Here you see the prediction from based different model, that's from Brown-Miller, Plasticity. You see all results are always in this region. That means prediction based on these models are not conservative at all. And you see similar situation, or rather scattering, rather large scattering, and the Liu model is also Liu model parameters present the best approximation. You see the scattering of Liu model 2 is not so, of Liu model 1 is not so large. That is double line, that is the 5-time line, and okay, that is actually more or less up to 2 points. The rest are within this 5-time line region. Okay, anyway. The effect of the TMF is not describable by the conventional model. What we see here is a TMF and TGMF difference. We can quantify again. That is actually the in phase here. That is the TMF and TGMF. That means we see also significant effect between just due to 20 degree temperature degree difference from internal side to external side. In reality, we said, what was said, the temperature difference between internal and external to internal can up to 100 degrees C. If we increase the temperature up to 1,000 degrees C. In that case, that means temperature difference is also very significant in phase, but out of phase seems similar again. That means the effect of the temperature gradient is also not uniform. Okay. Good. We come back again. What means we need actually a different model to describe it. For the purpose, we need even a new constitutional model for the case. The reason is actually we have rather complex loading history. Okay, therefore we developed a special model for TMF or TGMF. That is the situation here. Okay, that is the same. We used actually the on the one formulation, and that is the same as on the one suggested. That's also more or less the same, and with a modification by Khan introduced here, that introduced B. And the modification happens actually here. We introduced so-called algebraic hardening additional linkage. That is the 3 terms characterize actually the thermomechanical hardening additionally returned. And okay, this equation is actually introduced additionally, and that's the same as on the one, and then the rest remains all the same. And the results actually show us that is the comparison. Just show you one example here. More detailed results are published actually in a recent paper in International Journal of Fatigue. And you see the comparison between that's the peak value here compares between the different tests with results. Symbol show you the test results, color show you the experiments, and we have very good agreement between. Due to a complex situation, of course, you have slight difference actually. And you consider also very complex loading cases, stress over strain here. You use the shear stress or normal stress. You see that kind of cross form. It's the most complex situation. The model can characterize this kind of problem. Okay, then come to additionally to the fatigue model. We modify the model from Liu that's based on normal failure mechanism. And these are so-called virtual energy introduced or defined by Liu that is actually considered only in critical plane, the tensile strain energy and plus the shear strain energy in that plane. And that's a stability variable, and the rest is actually the more or less the sort of model. And then we added two weight term into it. And then modify this term is related with temperature gradient. These two terms are related with thermomechanical case, and then we just introduce actually the delta T is actually the average actually the temperature gradients, and then we consider actually this is actually more or less from idea of the Frobenius consider effect of fatigue. Creep, and then introduce this term into it. They found actually these results. These are all new model. That's all model what we introduced. You see, okay, main results are in actually within double line actually already. Okay, it is actually more comparison between the models. And this is a present model what we introduced. One is actually the best value. Is it all conservative? It's not conservative. Okay, one means exact. Actually, you see here scattering again. Okay, our model minimal scattering here, and so on. This is actually the results we'll show you. Okay, I conclude. The mechanical fatigue with temperature gradients and change materials behavior significantly, and the effect of TGMF and TMF have to be considered somehow properly, and the fatigue laugh prediction of TGMF has to be include both temperature gradients and phase angles into the model. That is actually we just show you, and the non-proportional loading factors based on temperature gradients provide significant improvement in the laugh prediction. The quantification of thermomechanical load effects need more detailed experiments and the combination efforts. The points actually become significant, especially for single crystal case. As I said, temperature gradient in single crystal becomes higher, and therefore that is actually what on you. So the last two slides. This is TBC specimen. You have sort of thermal bearing code specimen, and then you test the specimen under different conditions. You will see. Usually, if you have TBC, then temperature gradient could be higher. Okay, the difference between. Okay, that's it. Thank you.
Thank you very much, Professor Yuan.